Thanks for having me here. So today I'm going to be presenting an overview of the polarization properties of the published FRBs. Now, fundamentally, polarization is related to the presence or the existence of magnetic fields, and polarization studies are aimed at understanding these magnetic fields. But the raw polarization that we measure at the radio telescope could differ from the true polarization or the intrinsic polarization of the source because of effects such as propagation through the media between the source and the observer and instrumental non-idealities. Ultimately, we are interested in the true polarization of the source, which means that we need to be able to account for these effects. So the plane of polarization of linearly polarized light is rotated under the influence of an external magnetic field. So this is called Faraday rotation. The angle of rotation is the polarization position angle, and the amount of rotation undergone is quantified by the rotation measure. So depending on whether the magnetic field is oriented towards you or away from you, your rotation measure could either be positive or negative. So the polarization position angle can be measured from Stokes vectors, which are basically autocorrelations and cross-correlations of the electric fields that you measure at your radio telescope. Now, observations are typically performed over a large enough bandwidth so that you can actually measure the effect of Faraday rotation, but you also need to have fine enough spectral resolution to avoid appreciable rotation of the polarization vector within your individual channel, or else you're going to completely depolarize your signal. And we'll see that a little later on in the talk. And from this equation here, you can see that the rotation of the polarization position angle is larger with observing wavelength square. And like Brian mentioned yesterday, using a combination of the rotation measure and the dispersion measure, both of which are observables, you can estimate the average magnetic field along the line of sight. And again, this is a limit because you could have magnetic field reversals. Now, the RM that we observe is the sum of several components from different intervening media. So we've got an RM from the galactic foreground. You could have an RM from the ionosphere of the Earth, the IgM, the host, and the source. Now, the RM, due to the galactic foreground, can sort of be estimated. So we can look at the RM of the nearest extragalactic polarized source from the NVSS catalog. You could sort of try to estimate it from the closest known pulsar, or you could also turn to simulations of the Faraday rotation for the galactic foreground. And then, like Brian mentioned, you can also estimate the RM for the IgM from simulations. The ionospheric component is typically small. It's only appreciable at lower frequencies, and it also depends on the time of day. But on average, you don't expect more than 10 or 20 units of RM. So assuming that we can subtract the first three components, what we're left with is the RM from the host and the source. And for a source at cosmological distances, this is larger by a factor of 1 plus z squared in the source frame. So here I have a table summarizing the polarization properties of the published FRBs so far. And Liam's paper, I saw that just as Jim was giving his talk, so I haven't added that there. So of the 100 and odd FRBs, only 14 have published ones have full polarization information, and only 11 or 12 of them have RMs measured. So you can see that on average, most of them are highly linearly polarized. And while circular polarization is less common, you do see them in some pulses. And the third column, you can see that the observed RM is really sort of all over the place. Now, even the FRBs that are highly linearly polarized are quite diverse. For example, some of them have observed RMs well in excess of the galactic contribution, which suggests an ordered magnetic field associated with the host and the source. But then you have others which are, again, highly linearly polarized, but then the observed RM can almost entirely be accounted for by the galactic foreground. So this suggests that maybe there is no ordered magnetic field associated with the host and the source. I can better visualize this with the plot. So you've got a DM versus RM. The white dots are the pulsars. The triangles are the apparently non-repeating FRBs, and the squares are the repeating FRBs, and the star is the galactic center magnetar, and shaded regions enclose areas of possible progenitor space. And you can see that 121102 sticks out up there. And all the non-repeating FRBs are way down here and have RM values which are orders of magnitude smaller than that of the repeating FRB. Now, if you exclude these 3 points here from CHIME, you could have said that maybe all repeating FRBs have large RM values. But however, with the detection of the CHIME FRBs, we see that this is not really the case. So the proximity of the CHIME repeaters to the apparently non-repeating FRBs suggests that they possibly reside in different environments. So maybe they're not associated with active galactic nuclei. Or maybe the peak emission frequency decreases as the source ages. So potentially CHIME is detecting older repeaters. But I think we need a much larger sample of RMs to draw any sort of conclusion from this plot. So for the rest of my talk, I'm going to be focusing on particular FRBs because I think they're very interesting and they have told us a lot about what the sources or the progenitors could be. The first one is FRB 121102. So it's the first repeating FRB to be discovered. It is 100% linearly polarized with a negligible circular fraction in the 4 to 8 gigahertz range. It has an extremely large and variable Faraday rotation measure, so 10 to the 5 in the 4 to 8 gigahertz range. Until recently, this FRB was depolarized at 1.4 gigahertz due to insufficient spectral resolution. But now, from Laura's talk, we know that the RM has decreased to about 64,000 radians per square meter. I thought it was at 1.4. No. Is it at 1.4 or high? The RM? Yeah. No, the RMs are all measured at above 4 gigahertz. Okay, so that's not at 1.4. No. Okay, cool. No, sorry. All right, so well, the RM has decreased, and we still haven't got an RM measurement at 1.4 gigahertz. Is that right? Okay. Something to note is that typically in pulsar astronomy, you expect the polarization position angle to sort of vary with an S shape as the pulsar's beam crosses the observer's line of sight. But if you look at the pulses for the FRB 121102, the PA is fairly constant across the duration of the pulse and also in between pulses. And Jason in his paper has made interesting analogies to the high-frequency interpulses from the Crab pulsar. And you can see this, the high-frequency interpulses at 4 gigahertz are also 100% linearly polarized with a negligible circular fraction, and the PAs are constant across the duration of the pulse. You can also draw analogies to the galactic center magnetar. So the decrease in RM is similar to the decrease in RM of the galactic center magnetar. And the small projected distance of the galactic center magnetar from the supermassive black hole is again reminiscent of the association of this FRB being co-located with a persistent radio source. The next FRB we're looking at is 140514. So this is a very interesting FRB because it had no linear polarization but was highly circularly polarized. Now, we could look at 3 potential cases for why this could be. In the first scenario, maybe the source indeed has intrinsic low linear polarization and high circular polarization. We do know of sources like flare stars, brown dwarfs, AGN, and magnetars to exhibit circular polarization. However, flare stars and brown dwarfs have, on average, much higher circular polarization fractions. AGN have much lower circular polarization fractions than 21%. And magnetars, we can take the example of 1622. So this particular magnetar exhibits an infrequent state in which it exhibits high circular fraction with a lower than average linear fraction. In the second scenario, maybe this FRB is highly linearly polarized with some intrinsic circular component. But similar to 121102, if the RM is extremely large, then the signal could have just depolarized within your band at 1.4 gigahertz because Parkes does not have sufficient spectral resolution to be able to resolve the RM. In the third case, the circular could have been induced due to propagation effects, such as Faraday conversion. But I'm going to skip Faraday conversion because Andre is going to be talking about it next. The next FRB we're looking at is 110523. So this was the first highly polarized FRB at 800 megahertz. The circular fraction that you see here could almost entirely be accounted for due to leakage. Now, the reason this FRB is interesting is because this, so far, this was the only FRB to have a PA swing across the duration of the pulse, which suggests that this is a rotating star. So you could fit, you could use the RVM model that we use for pulsars to constrain an emission geometry. And in stark contrast, the pulses from 121102 are fairly flat across the duration of each pulse. But now we have pulses from the repeater at fast, so 180301 has PA swings, and also the one that Ryan showed has a PA swing. So maybe all this information combined could potentially tell us something more about what these progenitors could be. So the next FRB we're looking at is the one from CHIME. So this is highly linearly polarized again with a negligible circular fraction. What's interesting is that it has an extremely high RM, which suggests a significant host DM contribution. So this combination of high RM and low excess DM has led to the identification of a pair of merging galaxies at a redshift of 0.06, which they say could potentially be a candidate host galaxy, but I guess detection of a repeat pulse in targeted observations of this galaxy would help either prove or disprove this theory. The last FRB we're going to be looking at is 180301. So this FRB was detected at the Parkes Radio Telescope using 13-beam multi-beam receiver. It was only detected in one beam. And from this plot, you can see that the polarization structure is quite funky. Like the spectral feature at the top is highly circularly polarized, and then a little below that, you can see, there's a sort of flip in the sign of the circular. The RM spectrum showed 3 distinct peaks, suggesting that maybe Faraday rotation alone is not responsible for whatever polarization structure that we're seeing. So if you fit for this Stokes Q and U vectors simultaneously in the lambda square domain, you can see that neither a lambda square fit nor a linear fit are good models to the data, and you can see that quite obviously from the residuals here at the bottom. Now, I should mention that this FRB occurred during a 30-second transmission from a GPS satellite that was detected in the 13-beam receiver. It wasn't anywhere in the beam, but even a satellite tens of degrees away is still strong enough to be picked up by the receiver. So until recently, the nature of this FRB was still sort of ambiguous, but FAST has followed up this FRB, and from Bingstock, we've seen that this is indeed real. It is 100% linearly polarized, and the RMs are varying on daytime scales. I'm probably going to leave the discussion of this to the discussion session later, but I think over the last few days, there are several models which have sort of very elegantly accounted for the polarization that we've been seeing in these FRBs, and I guess the leading theory or the most favorite with everyone are magnetars. Again, with the interpretation of the RMs and the polarization, I think we need to consider these points. Now, scattering especially, because RM measurements are made on the assumption that the only frequency dependence to the PA arises from Faraday rotation alone, which in the presence of scattering is not really true, because simulations have shown that you can find RM variations where the PA swing is steepest. So this manifests itself as a flattening of the PA towards the latter pulse phases. I don't know, fortunately or unfortunately, the FRBs that we've had so far don't really show a swing in the PA, so we haven't been able to measure that. But also, we really need to be able to, or rather, we need to quantify the polarimetric variation of the beam of our instrument, especially for those FRBs that have not been localized too well. And I'm going to leave you with questions.